Hello, everyone, and welcome to today's webinar on robotic simulation and offline programming. I'm Steve Ruckhouse, Senior Digital Marketing Specialist at Yaskawa, and today I'm excited to kick off a live demonstration of our MotoSim EG-VRC robotic simulation software. MotoSim is Yaskawa's own simulation tool for Motoman robots. The PC-based software is designed for accurate offline programming of complex systems through our extensive model library, as well as the many built-in functions that can drastically reduce time, risk, and expense in setting up real-world robot jobs and cell configurations. And to give you an overview of the key features of MotoSim EG-VRC, I'm pleased to introduce Nelson Barksdale, Application Engineer at the Sim Lab here at Yaskawa. He'll be doing a live demonstration using the software's latest release. For those of you playing along at home, that would be version 2019 SP3. Nelson will spend about 35 minutes on the demo, then a Q&A session will follow. You can use the chat console to enter your questions at any time during the presentation. We are recording this session and we'll email everyone a link to the video later today. But before we begin, I'd like to run a quick poll of the audience that'll help our presenter get a read on everyone's prior experience with robotic simulation software. So you should see a poll pop up on your screen right now. And feel free to place your votes here. We'll give everybody a minute or so and share the results when everybody's had a vote. All right. Well, it looks like we have a pretty wide balance of experience with robotic simulation software. So hope that helps, Nelson. And we'll do a broad overview, but anytime you want to take a deep dive on something, feel free to ask a question in the chat console, and we'll get to those at the Q&A session. So now I will hand it over to Nelson, and we'll get things started.
Hello, everybody. I'm going to turn on my screen here. And I'm told there's a little bit of delay here, so I'm going to do my best to make sure I don't talk too fast. You should see on your screen a MotoSim. MotoSim, and it is MotoSim EG-VRC, yes. But typically, you'll hear everyone at Yaskawa just say MotoSim. We do actually have a second package known as MotoSim EG. It is designed, it's designed to support older robots, much older robots. So MotoSim EG-VRC that you see here, which I'm going to go ahead and start up this simulation so you can see something pretty on the screen. It is designed for our NX100 controllers, our DX100 controllers, our DX200, our FS100, our our YRC1000 and the YRC1000 microcontrollers. So anything from the past 10 years or so, it's going to support, well, more than 10 years, actually. I think more like, 14 years. Anyways, if you have a robot that's in the XRC or MRC or ERC, this software will not support, and that's where we have the MotoSim EG software. And if you have any questions, we can talk offline about that later. But for the rest of this conversation, we're going to talk about the wonders of MotoSim EG-VRC. And as you can see, you're seeing a simulation run on the screen right now. This is a sample this is a high detail. So if I were to maybe zoom in a little bit, you should see it's quite a bit of detail here. 3 robots are going to be welding. They are going to be working in conjunction with this positioner. This is one of our one of our carousel positioners. Now, the software is designed, has two main functions. One, it's going to focus on offline programming, as you've seen in the promo for this presentation. This is where you have a replication of your cell in simulation, and you're able to program the cell as you would in real life. The second main feature, and this is where I focus on, is concepts. What if scenarios? Can the robot do this? How fast can it go? Those are more of a pre-sales support, and many companies or our partners also will use it for that reason. For offline programming, the advantages are, let's say your cell is under construction and you need to have programming done. You don't need to wait for the cell to be finished. You can just start programming in simulation, and then you can pull the job files and the other data files out and put them in the real cell, and then do some basic touch up, because there'll be some variance depending on how it was assembled, or maybe the angle of your torch if you're using welding. The other area would be, let's say you are running, this is probably more common actually, you're running a part. Your part A is being worked on all day long. You need to work on part B. You need to program part B. Well, program part B in the simulation, save the files out, and put them into the real controller. When you're ready to run, do that run for part B. And that's also quite common. So MotoSim will also do functional safety. So we can set up functional safety. We can set up arm interference and safety zones. We can test for safety zones. We can't test for, let's say, light curtains. We can set those up, but we can't test for them because, well, MotoSim does function in a sandbox. So it doesn't, you cannot plug in a real world PLC into the software. So as you see, the robots are currently welding. I can show you. Let's see here. We go to the controller tab. I'll show you what the pendant looks like. So this is our virtual pendant. This is the upper half. If you're familiar with our line, you'll be familiar with our pendants. So you'll see this is a replication of the upper half. This is actually the controller virtualized inside the computer. So our cycle times are going to be very, very close to real world cycle times. Of course, there'll be some environmental factors that would cause a variance, but from what we've seen, about 2 to 3%. Here's the lower half. Oops. Move that over. There we go. So here's the lower half of the pendant. They are independent of each other, so you can move it around. So this is how you would interface with the robot in real life, and this is one of several ways you'd interface with the robot in software. MotoSim does have advantages over real world. We can manipulate the robot with a mouse, or we can manipulate it with a position dialog box, or what 3 other ways, offline picking. And I can walk through a few options and show you how that happens. But this is how it basically look. You can see that the pendant is on one screen, so I'm sharing one screen. You would probably want to have a second monitor, and I guess nowadays it's not a big deal. But we do recommend if you're on site or if you're at your desk, you have a second monitor. I'm currently using a USB monitor as my second monitor right now. So hide that lower half. In the simulation, we have various options we can work with. We have our position panel. The position panel here it gives you the ability to manipulate the individual axes, or I can change the configuration. So and I'll show you later, and I'm going to do a little walkthrough in a little while. But if you're programming to a point and the robot just twisted itself in the wrong position, you can actually have it change its configuration without losing your top point. And see, we have our CAD tree. This is where all our models are going to be. You'll see these are positioner models here. These are the robots. I'm sorry. This is the positioner. And then here are the robot models. So this is, if you're familiar with 3D CAD, like SolidWorks, this would be your feature tree. If you're familiar with Solid Edge, it's known as a Pathfinder. It's basically the same concept. Then we have the handle display. I'll show that in a little while. This lets you grab the robot and manipulate it directly with your mouse. Some people like myself, I'm a mechanical engineer in background, so I'm more hands-on. I have a colleague. He is a programming background, so he'll want to work independent. And we give you that option. We give you the ability to work in many different modes, whatever you're comfortable with. So on our controller tab, this is where you're going to fill out user frame information, our functional safety information, tool data. If you want to check the robot reach, we actually can create a robot reach envelope on the fly. And so you can see if the robot will roughly be able to reach a certain area without you having to manually test for that reach. It's like a quick check. On our simulation tabs, we have collision detection. It's a neat feature. If you're in a tight space, like some of these robots are, you can actually turn on collision detection to see if they're going to hit each other. I can show that briefly. 3D PDFs, really nice feature if you're working with customers. Under tool, we have our robot layout. This allows you to optimize a robot's position to optimize cycle time. Path planning helps you avoid collisions. And then we can do things like a difference report, safety fences setting, job conversion. This will let you convert your if you have a job from an older model, help you convert it to a newer model or a different robot. Our online function lets you connect to a real robot controller and monitor it, and then pull jobs off and modify and push them back on. And under option function, this is a very handy feature if you're working with situations with very fast cycle times. You might want to look at the duty cycle of a robot, the life of the reducers. This will help you analyze that. So I'm going to stop this real quick. Stop. It's got 3 robots, so it takes a little second to stop it. Let's look at a different simulation. I mentioned earlier about collision detection. So with collision detection, as you can see, we've got a cell here with 3 robots very close to one another, inches or less than an inch apart in some cases. In this simulation, they were picking up a collection of components to attach to these housings, and they were all connected. The robots have to work together as a team, but they can't hit each other. And it can be tricky when you try to manipulate and move a robot around. See, as you can see, I'm grabbing onto it here directly. And it's kind of hard to tell, am I hitting that robot or not? Oh, no, I'm not. Okay, but in this angle, I can't tell. However, with collision detection, they turn red. And I know they're going to hit each other. And this also, of course, will work when you are in playback. But boy, this was handy for this simulation. And let's see here, another one. This is a representation of one of our standard ARC worlds. If you go on to our site, our Motoman.com, go to software, you'll have an option for a model library, and we'll have a collection of components that you can either use, torches, or heck, we even have models of people. But we also have complete standard ARC worlds. So if you have bought one of our ARC worlds and you want to run a simulation inside of it, you can download a functioning ARC world simulation. And what you saw earlier is a variation of that. And you just drop your part in place and program the robot, and it will. You don't need to set the robot up. You may need to change the torch because your torch may be different from the ones in the simulation. But the hard work of getting the positioner configured and all the parts imported, it's all done. So this is actually quite handy. A lot of people ask for these. Now, let's see here. Let's show another example. This is a cool one. So this is what we call path planning. So here's a situation where we have a robot, a spot gun, and it's going to spot weld. I'm going to run this job. Hit start. This is the before. So as you can see, the robot is passing right through the fixtures. It knows its program points, but it's going to pass. It's just passing through the fixtures. Not recommended, especially when that thing weighs 115 kilograms. It's going to be a bad day. So what we do is, and we don't have the time here to actually walk through the process of setting up path planning. It does involve turning on collision detection, but I can show you the result. It's pretty cool. So let's go back. New job. Is used. And you can see the robot without me telling it to. I didn't have to tell it to what direction to move in. I basically told it, these are the parts you could collide with. Please avoid them. And it does. It works around them. It'll find its best path to work around the parts. And another example, we can do some conveyor tracking. So here's a conveyor that's running, and this is our MPP3S robot. It's one of our fastest robots. It can move at 3,500 millimeters per second. You're not seeing it move at that speed right now. That's just because of the internet connection and the graphics on the software. But yeah, this robot will move very, very fast. But so we can set up conveyor tracking. You can have parts in different positions, and the robot will then align those parts. And now you can also do this with painting. We have another feature here. I didn't cover that yet. It's called cam function. I don't have an example to show of that. We do have a video of that, though. That shows, basically lets you automate the process of if you're doing complex welding, painting, dispensing like glue. If you pick your path, the robot will automatically screw that one up. The robot will automatically program to that path. It'll automatically put the points in instead of you having to manually teach those points. It's very useful if you have a complex path. If you have a simple straight path, not so much. If you are into functional safety, we can also use functional safety in here. This is an example of that. So we have arm interference, tool interference envelopes. And you can modify all this data inside MotoSim and then export that to the real controller. So I've mentioned that a few times, exporting data. If you're familiar with our controllers, it's the same thing in real life. You basically will cursor over to external memory, and you will select save. And then from here, you can select job files, or you can select journal data, which would be your tool files. Also, your functional safety files will be here. But if I select a job, I would just select it and then save that out. Then that shows up in this folder that you can find it here at the top of the controller. That opens up inside of Windows. These are your different files, which you can then put onto a flash drive and put it to the real controller. And instead of saving, you would just select load. All right, from here, I think, I can show one other thing here before we get into it. I mentioned 3D PDF. So this is an example of a 3D PDF. The process of creating the 3D PDF is drop dead easy. You simply go over to Simulation tab and you select that button. You just push it. You can select options. You can go to the output settings and make a few changes. You can change the image. You can look at our company logos on there. If you want to change it, you can change it here. Put a title, any other information you would like. But in essence, you push that one button after you have created a job. It does need a robot and it does need a job. So once you create it, it shows up as a regular PDF file that anybody who has Acrobat Reader, and I do stress that Acrobat Reader, if you do open this in Firefox or Chrome or Microsoft Edge browsers, they will not read this. It'll show up blank. It does require Adobe's Acrobat Reader, which most business PCs have pre-installed. But as you can see, here's an image of it, but it's not an image. It is actually the 3D model itself. So I am currently working inside of Acrobat Reader, not MotoSim. And what's really cool is I can do this. So as you can see on the screen, the robot is animating and running through its routine. And as it's going through its routine, I can rotate the view, zoom in, zoom out, and get a better perspective. Down here at the bottom right corner is the playback time. That is the controller playback time. Please do not put a stopwatch to this. This is dependent on your computer's graphics capabilities. So the cycle time at the bottom is accurate. This is great for when you're doing presentations with department presentations, if you're working in the meetings, especially customer presentations. This is very, very handy. File size is going to be a couple megabytes. I did see one go to 80 megabytes, but that was a corrupt model. That was very, very rare. It's usually less than 20 megabytes for this. And most emails today have attachment limits of about 30 or more, and we all have Dropbox, so not a big deal. So great little tool, very easy to use. Everything I'm showing you, by the way, is built into MotoSim. These aren't extra add-ons. It's all included. So I'm going to start off, now that I've gone through a few samples. Let's go a little walk through here. When you launch MotoSim and you have created a new simulation, this is the screen you'll see. I also want a little side note. When you create a simulation, please remember that you are not creating a file. This is not like Microsoft Word. You're actually creating a whole folder. So this simulation is called CAD import. And when I go into creating it, which I can show you here, is just the application button. You say new, click new, and then it asks you for a name. And let's say I called it CAD import. Well, it creates a folder. And in that folder, it will create a collection of files. It'll create a models folder. And when I add a robot, it'll create a controller folder. So in the future, if you're ever passing your simulation to somebody else, please remember, do not send this one little file. This is the master file that controls everything else. It controls the location of the models, controls the location of the controller that it's for the simulation. But by itself, it's not much. So it's best to always remember to zip up this folder when you want to send it to someone else. So that being said, once you create the simulation, you will see a floor. We call this the floor, and you'll have the background, and that's it. So let's start with adding a robot. So adding a robot is actually adding a controller. So here's our controller tab. I'll select new controller. We have three options. We can start from scratch, where it says no file, which is what we're going to use today. If you happen to have what's called a cmos.bin file, that is basically an all-inclusive file from the actual controller. So if you have a cell you want to replicate in a simulation, you may want to go out to the controller and you would say to the inside the pendant, you would say save, and then you would go to the very bottom and you would say CMOS, click that, and it will send a single file. It's about 30 megabytes. And that one file can be used here to replicate the cell. So everything in the cell, the tool data, the jobs, the number of robots, they will all appear. Their graphical locations, however, will not. So you'll see the robots line up side by side, whereas in real life they may be in a different orientation. And it also is not going to show any positioners or any other CAD models. You'll have to add those manually. But the data for the job, data for the simulation will be there. So that's for the second option. The third option is if you wanted to connect to a new controller, a real life controller. So you have to be on the same network for that. A little more advanced. But for most people, they click the first option. We'll select OK. Now it's going to ask for a controller. So we have YRC 1000 micro, the regular YRC 1000, DX200, FS100, DX100, and X100 controller. Our current controllers are current robots. They're going to really be under the YRC 1000 and the YRC 1000 micro. Today we'll just use the YRC 1000. Here you can give it a custom name if you would like, and this is telling you your system version, the firmware of the controller. I'll select OK. This is a little new dialog box. If you are going to use a single robot and nothing else, then you use everything on the left side of this dialog box. If you're going to have more than one robot, or a robot in a positioner, a robot in a track, anything beyond a single robot, ignore this whole left side of the screen of this dialog box and just select maintenance mode execute. Anyone familiar with initializing a robot in real life will be familiar. It's the same process. But if you're working with a single robot, we can ignore the maintenance mode execute and just stick with this side over here. It's like an easy execute. So we'll just select both our languages. It does let you toggle between Japanese and English, but most people will probably just want to have one or the other. So we will just select English. And this controller group is our list of robots. So today, I guess we'll select the GP25. Then it's asking for application. Typically, we select general. If you select ARC or handling, and plenty of people do, those assign I/O specifically for those applications. But we'll just select general. After we select general, all we select is standard setting execute, and this starts it up. This will automatically initialize the controller, and it's done in the background, and you just need to wait a minute.
You still with us, Nelson?
Yeah, I'm here.
Okay.
Just waiting for the, here we go, for the initialization. I have to apologize. I have about, I think 7 simulations open. And I do have a workstation computer here, but even though it can still stress it. Okay, great. So this is our confirmation dialog. And the confirmation screen is going to confirm the CAD model that it's going to be pulling from. And we just select OK. And now it loads a CAD model of the robot. So now you see a robot here of the GP25. And of course, here is the pendant. So I mentioned earlier, there's a few ways to manipulate the robot. So I'll show you now. Most common way would be with the pendant. So we'll turn on the lower half. And of course, we can just use the pendant keys just like you would in real life. Now, just please note that it looks a little slow on your end, just the internet connection. It's actually pretty smooth. So we can use the pendant to control it. We can use the position panel. A few extra advantages here. We can automatically click and go back to home position. I can use pulse frame, which will move each axis one pulse count, which is really slow, but very precise. Mostly I'll select joint and that'll go by angle. So I can manipulate the S-axis that way. Another method, I will show that a little bit later, is called offline picking, OLP. This allows you to click anywhere that the robot will be able to reach to, and it will just go to that position. You don't have to jog it to that position. You can just click. These are what I consider advantages over real life, because in real life you would have to jog the robot. Here I can just click and it just snaps to that position. And we'll show that in a little bit. While we're at it, I can also show you the reach bubble. I'll do that actually once I add some models. Yeah, we'll do that. We'll do that also in a little bit. Let's go over to the other method, my all-time favorite. This is the handle display. This allows you to just touch the robot, and I can touch each axis and I can rotate it around. My favorite is manipulating the actual TCP, the tool center point. This is the teach point of the robot. So I can just jog it however I like. This is great if you are, let's say you're doing some concept work, if you're in handling applications. This allows you to very quickly move the robot in different positions. So I can click, move over here, then come into the position panel, record a point. Move back, come back in here, record a point. So I can just go back and forth, back and forth. If you're getting into something precise with welding, then you gotta be a little more cautious. So let's go back to home position. And why don't we go ahead and let's add some models. I'll hide this for now. There are several ways you can drag and drop. Probably a more direct way, especially if you're beginning in MotoSim, it would be go into your CAD tree and select Add. From here, when you want to add a model, you would select the model down here with the little 3 dots. And it's going to call open a Windows Explorer window. It defaults to the models subfolder of your simulation. So when you created your sim originally, it created the VCL file and a models subfolder. These are where your models reside. You can go and search somewhere else out on your computer and select a model there. It'll then ask you, do you want to copy this to your models folder? And you can either confirm or say no. When it converts that model type, it will, that converted version, the final version that you'll be using, it will be put into your models folder. But the other format, you can leave it out if you'd like. Let's show you the formats that you can import. So as you can, I'm not sure if you guys can read that clearly or not, but I'll read down through it. Hoops meta file, hoops stream file. These are the file types actually that are used by MotoSim. SAT file, that is a file type that is used in other CAD applications. That's also used in MotoSim. I stress to only use that though when you're using our CAM function. That's the file format required when you need to get a defined path, because it's actually using NURBS geometry. What you see on the screen right now is the HSF is a simplified tessellated geometry. So if you were to, you can't map a path for cam function with tessellated geometry. You have to use actual NURBS geometry, and that's where the stat file comes in. It does not mean that you should convert every model that you import as a stat file. If you do that, your sim's going to be huge. Stat files can be 10 times larger than HSF. So we recommend, highly recommend, that when you import a file type that you're going to use for cam function, it's only the part you're going to work on, not the fixture, not anything else in the simulation, just that one part. It's not going to break anything. It's just going to make your sim quite large. And if you're doing a lot of simulations, that could eat up your storage. So just take note of that. Other file types that you import, IGES, STEP. We'll do ProE files directly, CATIA directly, SolidWorks directly. But I will warn you guys, because this is, MotoSim is not partnered with SolidWorks or ProE or CATIA. Like any other application that's downstream of a CAD application, there's going to be a delay, 6 months to a year. So right now, SolidWorks' latest version, I believe, is 2021? Or no, 2020, I believe. Yeah, 2020 is the latest version of SolidWorks. It's actually out. We currently support up to 2019, I think, of SolidWorks. So, or is it 2018? I'm not sure. It's 2018 or 2019 of SolidWorks that we support up to. And in a future version of VRC, it'll upgrade to 2020. So just take note, if you have the latest greatest CAD, it may not import in. Typically, what I do is I save out to Parasolid files or step files when I import into MotoSim. But as you can see, yeah, we can do Parasolid. We also do Inventor part files, but not Inventor assembly. We can import DXFs, 2D DXFs, very nice feature. It lets you, if you don't have any 3D CAD, you can use a 2D drawing, convert it to a DXF, import that in, and then you can use that as like a skeleton to map out where the robot needs to go, and then you can extrude out some 3D blocks to represent those different locations. Not quite as accurate as a 3D model. It will take you a little bit longer because you have to build the 3D models inside of MotoSim, but if you don't have a 3D model, you don't. We give you an option to make it work, though. So quite a few number of formats. Again, these are all inclusive. These are not separate. This is not a separate package. This is all built into MotoSim. So for right now, I'm going to import a model called guarding. This is my primitive fence. And it gives it a name automatically. I'll select OK. This is the import dialog box. This is where you would select if you want to import it for cam function use or not. And it says here for cam teaching. Typically, don't check that unless you're going to use cam function, and only, again, on the part you're going to work on. So I'm just not going to check any option. I'm just going to select OK. So it goes through and it starts to import. This is a simple part, so it shouldn't take too long. Here we go. Here's the part. And you're thinking, oh, wow, it's not lined up. That's because this came from SolidWorks, and SolidWorks coordinate system has Y facing where Z is in MotoSim. So it's pretty easy to fix. What we do is just go over here in our CAD tree. We highlight the part. It's called guarding. And we come down here. This is our position dialog. And I just rotate about the axis. In this case, I want to go about the x-axis. So Rx, take it 90 degrees. And now it's in position. Maybe I want to move that. There we go. Now the key with replicating your CAD layout in simulation is that when you export from CAD, it's important that you export from the assembly that you're in for the most part. So if you have a whole cell, and let's say you want to export the fence, just suppress or hide everything that you don't need, keep the fence visible, and then save as a step file or save as a parasolid, your choice. Then hide that, and then unhide other sections. We don't recommend that you do this for every single little part. You don't need to do that. Just group it. The floor, the fencing. Now, the end of arm tool is different. End of arm tool, open that up in a subassembly, make sure its origins at the flange where the robot plugs into, and then when you import that into the robot, it snaps right on the flange. The whole point is to make sure all the parts are lined up with each other. If you open every single part in your assembly as its own part and then export, its origin may be in a different location than the assembly origin, and therefore it will not line up in MotoSim. You can definitely move the parts around in MotoSim. It's just that you have to guess. So if you want to replicate your cell, always work from the top level assembly. We do have videos on our YouTube channel that talk about this. So I'm going to get the next part now. We'll call this is going to be the work piece. And wait for that to import. Sometimes it does this. It hides it. I have too many simulations open. To rotate the view. Let's see here. Need to turn that robot. So I'm going to rotate the view of the robot 90 degrees. Now what I need is a tool. I'll show you two different ways. Well, you know what? Before I do that, we talked about the reach envelope. Let's show that real quick. So if we want to get an idea if the robot's going to reach or not, we'll go to the controller tab, click on TCP reach, so a button right here. We can check the P point or the tool location. P point of most robots is right here where my cursor is. I'll do a pause there for a second. It's right at the wrist because we don't know where your tool is going to be. It could be pretty far out there or it may be awfully close to the flange, but we're not sure. So P point is default. So I'll select the display to be a 3D bubble. I can do a 2D profile, but I'll select 3D bubble, and I'll just select create. Robot does a little dance for us as it's measuring. And there we go. Close. So now you can see this is everything inside this bubble the robot can reach to. I will warn you that anything close to the edge of the bubble, you'll want to verify, but you can get an idea. If your robot was too far away, you would know. This is the workpiece. It would be outside the bubble, and there's no way the robot would reach it. So anything inside the bubble and outside the inner envelope. So here's our outer envelope and our inner envelope. Anything between there, the robot should be able to reach to. Now, there can be different configurations, positions the robot needs to be in for whatever your application would be, and it may not reach. It may have an issue. You may be welding and you have to get into a pocket and you just can't bend the wrist of the robot far enough. That is always possible. So these aren't guarantees. They're just giving you an idea if your roughly in the range. So to turn this off, we go back into TCP reach and just select delete. Close this window. Now to create a tool, I'm going to expand the robot. So this YRC1000-R01 that you see in the CAD tree, that's the actual robot model. If I hit my little star key on my keyboard, it should expand it out, and you'll see these are all the different links that make up the robot. I select flange as the parent. Now the way we work here, if you're familiar with CAD, you're familiar with constraints. We don't have constraints in MotoSim. We have what's called a parent-child relationship. Anything that's a child, so this, for instance, flange is a part of the LK6 link. That is a child of link 5, which is our B-axis. The TCP is a child of the flange. Anything that's a child of something will move with it when the parent is moved. So I will select the flange to be parent. Now I'll just right click. I'll just say add. And here I'm just going to say test tool. You see I'm giving it a name. I'm not looking for a file. And I select OK. And it wants me to verify that I'm going to create a new file. This is a .mdl. This is going to create a 3D model, but unfortunately, it's ASCII text, actually. It's not a model you can export. So we've had that question before. Can I build these models in MotoSim and then export them? No, they are just actually text files. One reason, by the way, that when you do zip up your simulation, it compresses very, very well because most of the files here are text files. So now that I've created it, you can see it's highlighted. I'll just double click it, and I have this little dialog box pop up, and it wants to know, what do you want to create? I can do 2 different box types. I can do cylinder, a cone, sphere. I'll do a cone. Now keep your eye here on the flange. I'm going to say add. Oh, look at that. Little black cone shows up. Now I can define its diameter. I can define its height. I can define how many sides. Currently it has 16. I can change its color. So let's go to red. Oh, a little warning when you check on colors. When you're changing your colors, I will say be careful with red, because if you use collision detection, that can mess you up when you're trying to figure out if you have collision when the tool is already red. So a little warning there. Well, let's try purple. So the tool has been created. Tool data, however, that needs to be done. So I may want to tool TCP point out to this. Well, we want a little further out, don't we? So that when you're working on tool data, by the way, the top half, this is the actual tool data for the teach point. So it's angle, so the RX, RY, RZ, its position, X, Y, and Z. Down here, this is the mechanical data. This is very important for 2 reasons. In the simulation, it's important for cycle time. This is a GP25 robot, and I gave it no tool weight. So it's not thinking there's 0 tool mass. It uses default parameters. All our robots do this. They'll use a default parameter of the maximum tool weight that it can carry at a predefined distance for its center of mass. So in this case, this is a GP25. So this is going to assume it's carrying 25 kilograms right now at a predefined distance. I believe this is around 180 or so millimeters from the flange. And so these all may show 0, but they're actually not. If you want accurate cycle time, because most people aren't going to use the full mass of the robot's capability, then you'll want to put the weight in here, plus at the very least 1 field filled out for center of mass. That's important. That turns off the parameters. And then it will use these values. In simulation, I've found that the inertia values are not critical. They don't affect cycle time. In real life, they are critical. Please do not leave these. When you fill in your tool data in the real controller, everybody, please fill out every single field. You can get this from your 3D CAD model. If you don't have a 3D CAD model, go weigh your tool, estimate your CG, and use our calculations provided in our controller manual to get your moments of inertia. And we can talk all about tool data. A little bit of a passion of mine since I analyze tools for customers all the time. We want to make sure that your tool and our robot continue to work for the lifetime of that machine. So that's my little spiel. Let's move on. So you would fill this out, and then that will adjust your cycle time. Usually you get an improvement. Now, another method, and we're not going to use this tool. I just wanted to show you how you can build parts inside of MotoSim. But let's go ahead and turn this off. So I just right click and I can say hide C and uncheck model. And there it goes, disappears. But let's add a model from our model library. So the model library under home, this icon here, model library. Gonna hide that, get a little more room here. This is a library, it's on your hard drive. It has a collection of models that are already made up for you. We have additional models on our website you can download, and you can put them in your model library, which you can, by the way, define the location either in a hard drive or a network location. Oh, fun fact and side note, please. You can define your model library anywhere in the network. Please do not open your simulations from a network drive. Due to network lag, it can cause an issue. It looks scary. It's not, but we have seen it with a robot. It looks like a pile of junk on the floor. That's because the controller and the virtual pendant that you saw earlier and the main screen are actually two applications talking to each other. The network lag can cause a miscommunication. Just simply close the simulation. Don't save it, just close it, and copy it to your hard drive, reopen it, everything's fine. So make sure your simulations are running from your hard drive, but your model library can be on a network where you can share it with your coworkers. So moving on, let's go and pick a tool. Let's pick a Trigascus torch, why not? And we'll select this one. All I do is drag it over, touch the robot anywhere on the robot. I don't need to go to the flange. I can touch the bottom axis. It sees this is a tool. And because of that, it has tool data pre-applied. Now take note, see where the TCP is right here? Once I select OK, whammo, there we go. Our tool's been added and our TCP has been adjusted automatically. Isn't that cool? Trust me, you'll think it's cool. Because it takes a little bit longer when you want to manually add this. You need to take some of the time to attach the model to the robot, adjust the TCP. This is by its very nature. So being able to have this in model library is great. That being said, if you do have a custom tool that you put the effort into to create and attach to the end of the robot and you want to reuse it again, that's pretty easy. You come over here to the CAD tree, you right click on your tool. If your tool has several parts, make sure you've collapsed it and you right clicked on the parent like this, and you say add model library. Here you will define if it's a tool or a work piece. Just means like a block or anything that's not connected to the robot, just a plain old part. But if it's a tool, this is where you'll define, it'll get your tool data. So it'll preserve the tool data. You'll tell it if it's attached to the TCP or flange. I recommend flange. And just select OK. It takes a screenshot of the tool and sticks in your model library. You also, by the way, you need to define the category in the model library you want to put it in. And then you can just reuse it over and over and over again. Very nice feature. All right, so just for kicks, this can be helpful also. Where is that? Now, people. Sometimes we want to add a person to a simulation just so we can give a comparison on size. Oh, yeah, see, he actually has the whole thing. His whole body is segmented out. But we can move him. Out of the way. There we go. It gives you an idea just how the robot connects, how they compare to human being. Looks kind of nice. All right, so let's move on here. Go to controller and let's get the pendant back up. So if you're curious what I just did, I may have moved a little bit too fast there. Go to controller tab and select show pendant. If I have multiple pendants, I can show all. Oh, another little pro tip for you guys who are working on offline programming. When you're creating a simulation, make sure that you replicate your controllers, the number of controllers that you have in real life. So if you have 3 controllers for your cell, use 3 controllers in simulation. If you have 3 robots on 1 controller in real life, make sure you have 3 robots on 1 controller in simulation. If you try to create 3 controllers independently, you'll have a problem trying to get the data to work properly in the real cell. They'll all have the same name. The controller will be confused. It won't know which one to use. So if you have any questions, we can definitely help you with that. That being said, let's create a job. So we're independent. We select the job button, create new job, hit my space bar to get into it, and space bar again so I can type a name. We'll call it test. Okay, to acknowledge. Down here, the group set is which robot do you want to have this job connect to? Well, obviously we only have 1 robot, so R1. But if you had an R2 or an R3, you could select that, or a group of robots. Select execute. Now, let's change our move types. So this is a move J, joint move. That means the robot will figure out its own way to get and orient its axes to get to the location you're pointing it to go to. We're going to constrain that and use a move L for linear move. I do recommend when you're in welding, you'll almost always want to be using linear moves. It's more precise. If you are handling, you'll want to use linear moves for the fine detail. Like if you're approaching the part you're going to pick and place and drop off locations, you'll need to use linear moves for that. And but the transfer point, you can use a joint move, it'll be faster. But for here, we're just going to trace this box. So we're going to stick with linear. So I'll open up the lower half of the pendant, change the motion type to linear. You can see it went to move L. Gotta make room here. And change its speed. We'll go 1,000. In real life, I know we're using a torch on here, and no, we would not go 1,000 millimeters per second. That would be insane. Now I can use the handle display to move the robot to this position, or what I can do is go back and use this OLP dialog that we looked at earlier. Do pick enable. And that allows me to select a point. There we go. Wherever the red arrow is pointing down, there we go. The robot selects. I didn't have to jog the robot. I just click and it snaps to that position. So now I just hop. So I move my mouse into my virtual pendant, and I have my move type to L. My speed is set to 1,000. I just hit enter. Ow, that hurt my ears. That's because I didn't have servos on. There we go. Turn the servos on. Now, there we go. I'm not sure if you guys heard that. It was an error beep, and it was a high-pitched beep, and I have my headphones in. So really just going to move around the simulation. Let's move over here. Rotate. Oops. And the next point. Move back independent. Hit enter. Next point. And do it again. And go back to home, the starting point. Click. Enter. Now, sometimes when I use OLP, offline picking, sometimes the robot likes to change its, and for some reason, it just puts itself there, and it may twist itself in the wrong configuration. And I'll show you what that looks like. So close OLP, open up the position panel. This is our configuration button. These are all the different configurations the robot can be in. As you can see, it keeps changing its configuration, its position of its different axes. It's still touching the top point, it's just how it got there. So if for some reason, let's say it was this configuration, and then on the next point, see the Yaskawa logo was upside down. On the next point, the Yaskawa logo was right side up. Well, that could be a little bit of a problem. Yeah, what will happen is the robot will twist itself to get to the next point, and you don't really want that. That's why we have the configuration button. You can change the configuration to make sure it matches the other top points. So it's a nice smooth transition, and then you can modify those points. You would move to that top point, and then you would simply open up the lower half, the pendant, and just modify enter. So you would select the configuration, select OK, then modify enter on that top point. But in this case, everything worked out great. It actually, the orientation of the robot is consistent. So that being said, created this simple job. Go to play. If I click on display cycle time, now you can see the playback time of the robot. And I just select start. And you can see the robot move through the different top points. It's going around and done. All right, so it did this in 2.81 seconds. But there's more. What if we want to optimize that? I want to move that robot somewhere else. I think that robot can do this faster. Maybe it can. So I can sit here and move the robot. So I can move this robot any direction I want and go to utility parallel job shift. This is a programming feature. This is not unique to MotoSim, by the way. Parallel shift is in the real controller, if you're not familiar with our controllers. And I can move the robot and then shift the job opposite the direction I move the robot to bring it back into its into its top position. I can do that over and over and over and over and over again, and it can take me hours. Literally, it could take hours. We don't want to do that. Don't want to do that at all. Time is money. Let's go to simulation. Oh no, let's go to tool. Layout robot. I'll select that. This is going to iterate the robot's position, teaching those same points over and over and over again. It's going to automate the process of what I would do manually. All I need to do is select the job, which I did. I only have one job. And I give it a layout area. How far in X, how far in Y, and how far in Z. And then what's the grid pattern going to look like? What's the grid interval going to look like? So we're not going to worry about Z. This, by the way, if you get too detailed, if I were to select, I don't know, 100 by 100 and a grid of 1, go take a break. This is going to take a while. The software is going to iterate over and over and over in every potential configuration. So I'm going to select 200 by 200. Leave the grid at 100. A couple options down here. We can click, if we check this button to update monitor, you'll actually watch the robot iterate. If you do that, though, it will slow down the process further. Or I can check this box, rough search. Now, the rough search is less accurate, but it is faster. So if you're in a rush, you could use this option. Just check this. So, but the configuration I've checked here, it shouldn't take more than about a minute. So we'll just select start. You'll notice that the pendant will be going through a series of calculations. It'll just run through the job over and over again. And on this screen, I'm going to move this over. You'll see a number of options show up showing the different configurations that worked. If it doesn't, if the robot's too far away and it fails, it will not show up in this white area here. Let's start. And now it goes through the different calculations. And all it's doing is iterating, moving the robot 100 millimeters in a grid that's 200 by 200. And it doesn't, negative and positive. As you can see, we were at 2.81, but now look, now we're seeing 2.77. I know that's not much. This is just an example, but sometimes it can mean something. We have plenty of customers who a tenth of a second is important. And it continues. There we go. Process is complete. So now we have this listing of different configurations that I can step through. So I can just, as you can see, I just take my cursor on my keyboard, all I'm doing, and going through all the different options. If I had selected Z, this would take a lot longer. So that's why I didn't select it. But it doesn't require my time in front of it. So I can be busy doing something else. So we'll just select this first one here. All I do is select OK. And then what's going to happen is it's going to adjust the robot's position to this new location, and it's going to adjust the job. Done. So I'll just hit play, start. Oh, see, it inverted the robot. Darn it. Well, I swear it was working a minute ago. And it always happens. Ah, darn it. That's gonna not. It's trying to turn under itself. Well, anyways, it does work. Trust me. It's 2.77 seconds would have been the cycle time for that. So I think that would pretty much conclude my little presentation here of what the different features are of MotoSim.
All right. Well, thank you, Nelson. I know we've getting a little bit short on time, but if you want to keep your screen sharing on,
Yes.
I can go through some of these questions that a lot of them were asked earlier, and I think you did cover them, so we can kind of browse through them really quick. We had one question come in early. What is the accuracy error between offline and online programming?
We've seen about 2 to 3% as long as you have adjusted the real cell to the virtual, or the virtual cell to the real cell. So the real cell will usually be off a little bit because of tolerant stack-ups. So creating a user frame on the real cell and then bringing that into the virtual cell and adjusting your models to match that can fix that. Or you can just, if the variance is very small, you just do a touch-up. But when it comes to cycle time, if you were to take a single robot, barring that the robot is not already is in good condition, it's not an old robot and is greased properly, we've seen 2 to 3% because we're actually using the kinematic modules that are in the real cell.
Okay. Another question: are there alarm codes and explanations in the software as well?
Yeah, there are alarm codes. The alarms are going to be the same alarms you'd see in real life. So there'll be some basic explanations in the bottom of the pendant.
Okay. Does the pendant window work with a touchscreen monitor?
Yes, kinda. We've actually had some people who have some touchscreen laptops. It's not really designed for it. If your mouse can click on it, though, your stylus probably can too, or your thumb. But you may find it a little bit tricky. But it should kind of work.
All right. You might have covered this, but is there monitoring of self-collision? And may as well talk about singularity while you're at it.
Well, self-collision of the robot, the robot's not going to hit itself. It is if I jog the robot, it does have angular limits to each axis, so it's not going to hit itself. As for singularity, singularity is an issue that it's better over time. I mean, the software, if you have the robot inverted, you can run into a singularity issue if it runs underneath its center of mass. If you have the fifth and fourth axis lined up, you could run into singularity, but it's become less of an issue. It doesn't happen quite as often now.
Okay. Another question, just to clarify the import mechanism, is that only from items in our model library, or can they import other things such as self-designed machines, conveyors?
You can import whatever you like. If you guys saw the cover slide on the intro to this presentation, all those models were imported in from, what was that, Autodesk Inventor? So those were all foreign models. It just needs to be one of the formats I mentioned, and it'll import in, barring that you don't have corrupt geometry. That's a whole side topic, by the way, outside of MotoSim, that I could spend too long talking about. And if you have questions on importing, feel free to contact me.
All right. Thanks. We also had a question about collaborative functions. Are they available on the current release of MotoSim?
So we have collaborative robots available, collaborative functions. No, the collaborative the collaborative robots work with either scanners or torque sensors that are into the robot, and those are the real robots. The simulated robots don't have torque sensors inside them. Even then, it has to detect an object. So it has collision detection. If you want to simulate collaborative, you can simply just turn down the speed of the robot if you'd like, and then it'll slow itself down that way.
Right. Wayne asks, can you optimize speed and cycle time based on tool data?
Oh, yes. Very much so. I've seen 9-10 second save sometimes. I actually had a demo. We're running out of time, but it only shaved like 1 second off from the configuration I had, so it wasn't that dramatic. I do have a simulation somewhere where I had a sim where it was like 20 seconds for the cycle time, and when I put the right tool data in, it dropped down to 9 seconds. So yes, tool data, very important for cycle time.
Okay. There were a few questions about I/O.
Okay.
Is there a way to use, one question was, is there a way to use I/O connection for press handling projects?
You can set up I/O for anything you'd like. You can't test I/O. I can create inputs and outputs to my heart's content and configure it. I just, that PLC that's sitting out there, I can't connect to that. But you can program for all that I/O.
Okay, so you're simulating signals and handshakes?
You can simulate that, yes. You can simulate that. We have a whole other feature in here that's model scripting, non-model scripting, and it basically allows you to simulate the motion of machines and the motion of grippers opening and closing. We can do all of that in MotoSim, and we can tie those to outputs. So you can create the output and at the same time run that script. And the script would be for the simulation only. You don't need it in the real world, obviously, but you can simulate it that way. That's a whole other topic.
Okay. Josh asks, can you add a 7th axis linear rail?
Yes. Yes, that's part of the, so in that case is where I showed you guys how to import a CAD model, or a CAD model, how to set up a controller. And there was a button that said, for the button I mentioned on the right-hand side for advanced, that's what you would click to initialize it. And there you would set up your rail. You will need to have all the mechanical specs for that rail, because if you don't, it won't know, how far it can go, how fast and accelerate and decelerate. You'll have to know all that ahead of time. But yes, you can definitely do that.
All right. And somebody wants to know the default number of inputs, outputs in the YRC 1000 controller.
Oh, that I'm sorry, I can't answer to.
Okay, that'll be on the data sheets.
It's on the data sheet, yeah.
On motoman.com. Well, I think we got through most of the basic questions. I want to thank everybody for sitting through, and I hope you learned a lot, as I did, about the MotoSim software. If we will be providing a link to the video recording of this presentation. When you enter the room to watch the recording, there will be an opportunity to ask Nelson some additional questions through a contact form on that page. And that will be the best way to make sure that you have all your questions answered. In the meantime, we are going to go ahead and wrap this up. I want to thank everybody for attending, and hope to see you at the next Yaskawa webinar.